All right, welcome back. We're going to be looking at the application of making alpha halo compounds that we saw at the end of the last video. So to kind of review, an alpha halo compound can be made from a ketone, like so. So if we take acetophenone and we react it with acetic acid and bromine. Now, again, this is an acid, so we're just going to get the monohalogenation at the alpha position. So to recap, we have an alpha position there and an alpha position there. And the only one that is viable is the one on the right. And the reason why is because it has hydrogens that can be abstracted from this alpha position. All right, so we're going to add the bromine to that alpha carbon. All right, so there we go. Now, what's very interesting about these, what we call alpha bromo compounds, and the reason they're called that is because you have a bromine at the alpha position, is that they are very good, what we call SN2 substrates. And what that means is we can use nucleophiles to attack at that alpha position. So we will draw our alpha halo compound here. And if I react this with sodium cyanide, right, we've seen sodium cyanide several times. It's a very good nucleophile, and it can establish a carboxylic acid derivative when used in SN2 fashion. So this will be like an SN2 substitution. And now what we're going to get is a cyano group in the place of the bromine atom. All right, so SN2 displacement of the bromine gives us a cyano group there. And of course, there's a lot of rich chemistry with the nitrile, or what we call the cyano group. All right, so I'm kind of expanding out that CN to show the CN triple bond. And I can hydrolyze this guy if I wanted. All right, so hydrolysis of a nitrile. A nitrile, again, is a carboxylic acid derivative. So that will actually hydrolyze it by definition to a carboxylic acid. All right, so let's just keep track of where everybody came from here. All right, so we have this carbon here, we'll call carbon 1. We have the alpha carbon there, and then we have the nitrile carbon that we'll just call carbon 2. All right, so we number everybody, 1 alpha carbon 2. All right, so again, we've hydrolyzed the nitrile to give a carboxylic acid here. All right, so very useful transformation in synthetic chemistry. Also, we can look at these alpha halo compounds. Let's go ahead and take bromine and acetic acid again. All right, so we're going to get monobromination. Oops, not a benzene ring. Here. Now, if we take a base, we can actually promote what we call an E2-like elimination. All right. So again, here's the alpha position, and down here's the beta position. So if you recall, E2 eliminations are what we call beta eliminations. So that was where we would form a double bond between the alpha and beta carbon. And one way that can be done is with something called lithium carbonate. Lithium carbonate is a good base for these type of elimination reactions. And what we are going to get is the following compound. All right, we get an alkene in the place between what we call the alpha. Oh, that's not a good looking alpha, is it? Alpha and beta. All right, so we're getting the pi bond there, and it is a ketone as well. So this compound right here is called an alpha beta unsaturated ketone. Right, and these are very handy as SN2 prime substrates, or what we call Michael acceptors that we're going to see in a later chapter. All right, so this is a good way to make these alpha beta unsaturated ketones. All right, so we've seen two handy applications of having these alpha bromo compounds. All right, the next thing I want to look at is what we call the direct alkylation of enolates. So this is a very handy reaction in the fact that what we're going to be doing is making carbon-carbon bonds, right? That's what we imply by saying alkylation. But this is almost exclusively done through the enolate, all right? It turns out it doesn't work so well with enols, all right? So this is a little more specific to enolates. And what we're going to be looking at is if we take a ketone, for example, and we're going to go ahead and draw this alpha position. And again, if we're going to make an enolate, what we need is base. All right. So this is going to be a two-step process where we're going to take a base. I'm just going to have a generic one here, B minus. And we're going to take an alkyl halide, Rx. All right. So it's been a while since we've seen alkyl halides. The R, of course, is the alkyl portion, and the X is the halogen, or which would be a good leaving group. All right, so bromine, for example, would be a perfectly good example of X. All right, so what we're going to do is we actually add the R group to the alpha position, right, in this two-step process. All right, so this will give us the alkylation at the alpha position, but we have to do this through an enolate. All right, so what I want to do now is go through the mechanism of this process. So we'll go with the same ketone I drew in the previous slide. And we're going to go ahead and draw the alpha hydrogens there. And I'm going to take a base. And in this case, we'll use LDA. All right, this is often the base that is used. So it's lithium diisopropyl amide. So this guy right here is LDA. All right. And what it's going to do is form the enolate irreversibly, and that's important. All right, if it's reversible, this reaction does not work very well, because what ends up happening is if it's reversible, the base will end up attacking the electrophile in the next step. So typically when you want to do these direct alkylations of enolates, you want to have a non-reversible deprotonation in the first step. So LDA, and we want this to be typically cold. So minus 78 works beautifully in most of these reactions. All right, and this reaction, nothing's going to happen. All right. When we get to this product, nothing's going to happen unless you throw in an acid or an electrophile. All right, throwing in an acid would be kind of silly because all you would do is go directly in reverse, right? You would just reprotonate the enolate. But what we want to do now is we want to add an alkyl halide. And one of the best alkyl halides for this is something called iodomethane or methyl iodide. All right. So methyl iodide is a liquid. It's a very reactive electrophile, and it's a good source of a methyl group. And this would be irreversible as well. All right, so there is our alpha alkylated ketone. All right, so the typical recipe is going to be LDA negative 78, and we're going to put in the alkyl halide in the second step. Now, there are situations when you can get away with a thermodynamic enolate, all right? So I know I just went and was talking about you want it to be non-reversible. That's the best case scenario, right? You're going to want to do it that way. However, we can look at something like this. Well, let's not jump ahead. Let's just see how this guy would work, all right? So this is the molecule benzyl cyanide, all right? And it has an alpha position, all right? So it's a little complicated sometimes with these nitriles. All right, remember nitriles are these pseudo-carbonyl containing compounds. All right, alpha to them, they are also enolizable. All right, so the way I want to draw this out is I'm going to draw the triple bond in the lone pair on the nitrogen, and I'm going to put my two hydrogens in the alpha position. And I can take a base here and make the enolate anion equivalent of the nitrile. All right, because what you could do in a subsequent step after you've generated this nitrile is you could throw in an alkyl halide. All right, we're just going to have a generic Rx here. And we can alkylate the cyano group alpha in the alpha position. Pardon me. We can alkylate in the alpha position to a nitrile. All right. So the next step, I'm going to show that product. All right. So there's our alpha position. Okay. Now, we can do this two ways. So just bear with me here. We're going to look at what we saw before. So if I were to take LDA, negative 78, and I take iodomethane, all right, so what's going to happen here is we are going to generate the enolate anion equivalent by using the LDA, negative 78, and then we're going to alkylate at the alpha position using iodomethane. So what we'll get here, apologies here, let's try this again. All right, okay, added the methyl group in the alpha position. I can change this up and go to thermodynamic conditions. I can add something called sodium hydride. Now that is a very strong base, all right? However, we're going to do this not at negative 78, but we're going to do it at room temperature, all right? So now what we're going to do is we're going to have enough thermal energy to get over an activation energy barrier, all right, and have thermodynamic conditions. All right, so in the case of thermodynamic conditions, what's going to happen is we are going to alkylate twice, all right? And the reason why is because once you make the product, it's a thermodynamically more favorable enolate to make than it was in the beginning. So you're making a more reactive intermediate, if you will, and it's going to continue to react. So we have to be careful here. We need excess of both the base and the alkyl group, or sorry, the alkyl halide. So what we'll get here is what we call exhaustive alkylation of the alkyl position, all right? So if you just want to have direct one-time deal alkylation, go LDA minus 78, then throw in your alkyl halide. If you want reversible conditions, then what you're, thermodynamic conditions, what you're going to want is sodium hydride at room temperature and then methyl iodide. And you want excess of both of those, and you're going to exhaustively alkylate at those positions. All right. So to wrap this up, I want to look at a pretty cool little intramolecular puzzle. Now, I'm a big fan of these intramolecular cyclization reactions. I just think they're fun. You know what? I'm having a bad pen day. Better. All right. So what we're going to do is we're going to have an alkyl chain here, and we're going to have it terminated with a bromine atom. All right. So what I can do now is I can treat this guy with LDA at minus 78 degrees C. All right. And what's going to happen there? Okay. So let's take a look at this. Going back to the two schemes below, if I take an enolizable molecule and treat it with LDA, I make the enolate, and then it reacts with an alkyl halide in the second step. So I'm talking about this top reaction here, all right? Now, if I'm here, well, LDA minus 78, that's going to make my enolate, but what's cool about this is I already have an alkyl halide built into the molecule, all right? So this is going to be an intramolecular reaction. So the question is, which enolate do I form? All right, I have the two alpha positions here, alpha 1 and alpha 2. All right, so LDA negative 78, that's going to favor which enolate, kinetic or thermodynamic? And the answer is kinetic. All right, so we're at low temperature, irreversible conditions. So we're going to go after the alpha position that is more accessible, easier to get to, and that is alpha 2. All right, alpha 2 is your kinetic position. All right, so what's going to happen there is you're going to make the enolate. So we're going to have alpha 2 here, alpha 1, then our built-in alkyl halide. So I'm going to go ahead and number these guys. 1, 2, and 3. All right. And then I'm going to say this guy is carbon, let's just call it 0. All right, over here. What's going to happen is you're going to have an intramolecular reaction. All right. So what bond am I going to be making here? I'm going to be making an alpha 2 to carbon 3 bond. All right. So my question is now, how big is that ring? So I'm going to draw green dots to indicate the carbons, or well, in this case, carbons, that we are counting to make this ring system. So we got 1, 2, 3, 4, 5, 6, 7. It's going to be a 7-membered ring. All right. So to draw that, I make a cycloheptane-like ring, and then I'm going to go ahead and label these guys. So this was alpha 2, this was alpha 1, and between them is a carbonyl. All right, and then alpha 1 was connected to carbon 0. Carbon 0 is 1. Carbon 1 is then attached to 2, and carbon 3 is attached to carbon 2. All right, and then carbon 3 is attached to alpha 2. Cool, so we got our 7-membered ring there. All right, and let's not forget, I'll do them in red, our 5-membered ring that was already there. So we got 2 green dots on alpha 1 and 0, and I got a guy over here, a guy here, and a guy here. So I need to draw those guys there. All right, so pretty cool, huh? We get a 7-membered ring fused onto a 5-membered ring. All right, now how would you get alpha 1 to participate in this cyclization? All right, well, alpha 2 was what? The thermodynamic, the kinetic enolate. So alpha 1 is going to be the thermodynamic enolate. So how do we get thermodynamics to do this? Well, we could take the same starting material, have alpha 1, all right, and then we'll have our alkyl chain, like so, all right. We got carbon 0, 1, 2, and 3. And what do we need for thermodynamic conditions? Well, we could use NaH at room temperature. All right, we saw that just today. So we're going to form the thermodynamic enolate here. So there's alpha 1, carbon 0. All right, and this will collapse. We're going to get nucleophilic attack here and kick off the bromine. So now with the green dots, I'm going to count how many carbons are in our ring. Got 1, 2, 3, 4, 5, 6. Pardon me. This guy's not in the ring. It's on the outside of the ring. Oops. All right, so we actually get what? 1, 2, 3, 4, 5. So it's going to be 2 5-membered rings fused to each other. And let's count them. This is alpha 1, 0, 1, 2, and 3. All right, so where the heck is our oxygen? Well, it is out here. All right, so we get the methyl ketone on the outside. So 2 5-member rings fused together, and then we have a methyl ketone off the alpha 1 position. All right, so this is pretty neat. You can get 2 different products depending on what base you use. So let's just kind of recap this whole process. I'm going to start with the 7. Okay. And the other one, so this was the kinetic, and this was the thermo. And it just depends on what kind of base you're going to be using, all right, and temperature conditions. So kinetics, what do we want? Something strong like LDA, minus 78. And for thermo, we want something like sodium hydride at room temperature. All right, so those are going to be very important skills to understand, knowing that you're going to have a reaction through kinetic or thermodynamic. And I left off one important piece of the starting material there. You need to have the alkyl chain. All right. Well, that's a good place to end up. We've now completed our discussion of the reactions at the alpha carbon. All right, so we have halogenation and alkylation. What I want to get into in the next video are going to be condensation reactions of carbonyl-containing compounds. Take care.